Okay, this lecture will supplement Worksheet 2, dose distribution. So let's start with number 1. For a 9 MeV electron beam, please state the following. The range of maximum depth. In order to get the range, which means as far as all of the dose will go and none of the electrons will get further, always divide by 2. So 9 divided by 2 equals 4.5 cm. To get the 80%, you want to divide the energy by 3. So 3 cm is where 80% of the dose would go. And if I were to ask you where would 90% of the dose go, always divide by 4. And that's where your 90% isodose line would be. For number 2, list 3 sites that electrons are commonly used for treatment. Electron boost for breast, anything that's superficial that we don't have to treat that deep. Lymphatics, skin lesions, IMC, that's the internal mammary chain, perineal boost, all of those things would warrant electron treatment. The useful maximum depth of electrons, this is pretty much the depth at which they are most useful. And according to your text, 5 to 6 cms. Beyond 6 cm, then you need to start thinking about using photons. So they say the useful maximum depth of electrons is 5 cm. Number 4, the minimum thickness of block needed for an electron energy of 22 MeV. Rule of thumb, if you want to find it for lead, divide the energy by 2. Oh, and I have 22 MV, and I apologize. This should actually say 12 MeV. I have it typed in wrong. So divide the energy by 2, and that's the thickness in millimeters of lead. To get the thickness in cerebin, add another 20% to that. 20% of 6 millimeters is 1.2, so 7.2 millimeters in cerebin. 5. The transmission of the primary photon beam through a cerebin block must be 5% or less. So as a rule, the block must be able to attenuate 95%. Multi-leaf collimation is even better. That can attenuate 99.5%, so that's even better. But for a cerebin block, it must be able to attenuate at least 95%, so only transmitting of the beam. 6. For a hinge angle of 60 degrees, name the wedge angle. The formula for wedge angle is 90 minus hinge angle divided by 2. So do your formula out. Let's see, 90 minus 60 over 2, 90 minus 30. So your hinge angle is 60 degrees. Or excuse me, your wedge angle. Wedge angle is 60 degrees. And remember, definition of wedge angle. Here's the skin surface right here. Here's your isodose lines. The wedge angle, if you draw a line parallel to the skin surface that you see right here, parallel to the skin surface and perpendicular to the central ray, draw a line, that's that line right there, and the angle that it makes with your 50% isodose curve is your true wedge angle. What is the hinge angle for a beam having a 15-degree wedge? Hinge angle formula. Hinge angle equals 2 times 90 minus the wedge angle. So 2 times 90 minus 15. Hinge angle 2 times 75. Hinge angle is 150. Hinge angle is the angle between the central ray of 2 wedged beams. So let's say I'm treating somebody's head and neck area and I have one beam coming in at this angle, and let me erase that. I didn't draw that like I should. Okay. There's one beam, there's its central ray coming in, and say you were treating from this angle as well, and there's its central axis. It's the angle between the two central axes from both beams. It's hinging. Number 8, what is the percentage depth dose for a beam with a dose of 250 at Dmax and a dose of 200 at a 5 cm depth? Formula, percentage depth dose. The dose at a depth divided by the dose at Dmax. So percentage depth dose for this guy would be 200, because that's my dose at 5 cm, divided by 250. So your percentage depth dose, and always multiply that by 100 since you're giving it in percentage, is 80%. And remember, percentage depth dose is a comparison of the dose that I get here compared to my dose at Dmax, because Dmax is where I'm getting 100%, and after that, any deeper, my dose goes down. So what percentage is this dose of my 100% that I have prescribed? And remember, if you hear the term given dose is the same as the dose at Dmax. That's how much we are giving. Number 9, a dose of 180 centigrade is delivered to a depth of 7 cm on a central axis with 6 MV beam having a field size of 10 by 10, 100 SSD. First of all, A, what is the dose deposited at Dmax on the central axis? How can I get dose at Dmax or dose at a depth? I use my percentage depth dose formula. But for this problem, I didn't give you the percentage depth dose, because for percentage depth dose, it's dose at a depth over dose at Dmax. I gave you the dose at a depth, but that's all I gave you. So use your table. Make sure you're looking at a 6 MV beam, 10 by 10 at a 7 cm depth. Your percentage depth dose when you use your table, 79.1. So now let's just fill that into our equation. 79.1 equals my dose at a depth, which is 180, over I don't know what my dose at Dmax is. Once I do the math, dose at Dmax equals 228 centigrade. So all I'm doing is I'm using my percentage depth dose formula to get that. Now B, what is the dose deposited at 12 cm? So again, I can use my percentage depth dose formula, but I'm going to use different values. My Dmax stays the same, because that's for this beam. That's going to remain the same. That's the dose at Dmax at 100%. So that's the same no matter what depth I'm talking about. So I know what my dose at Dmax is. So if we write that over here, it's 228. Now, I want to know what my dose is at a depth. So that's going to be X. What I can look up is my percentage depth dose. Now I want to re-look it up on a table because I want to look it up for a depth of 12. When I looked it up for A, I looked it up for a depth of 7. I want to now look at it for 12. And when I look that up, 60.9 is my percentage depth dose. So if you set the formula up as so, X equals 138 centigrade. And that's how much dose is getting at 12 cm. Number 10, for the following rectangular fields, determine the equivalent square size. I asked you to get it by using the table, which is called the tables of day, and calculating. So I'm not going to do it with the tables because I think we were all very good with that. But let's just go over how we find equivalent square using a calculation, and that's Stirling's formula, 4a over p. So for this first guy, the area is 66, and the perimeter is 34, which is giving me a 7.7 cm square. For B, my area is 150, perimeter is 50, 12 cm. And for this last one, we have 4 times 216 over 60, and that gives you a 14 cm. For number 11, find the equivalent square for the following blocked fields. So now with this, we have to take into consideration the actual field and what's blocked. Okay, so step 1, for a 20 by 20 field, the total field size, let me erase that because that's scribbling there. All right, the total field size, it's a 20 by 20, so that's 400. Step 2, the blocked field on this is 10 times 5, so that's 50. So if you take the ratio of your blocked field over your total field, it's 50 over 400, and that equals 0.125. Now you're ready to do your equation. Your equation is the field size of the total field times a square root of 1 minus the ratio of block to open field. And when you do that out, that's step 4, the answer for that should be 18 points. So for our next one, step 1, the total field is a 10 by 10, so that's 100. The blocked area is 16. We take a ratio of that, 16 over 100, so the ratio is 0.16. Let's do our equation. So the field is a 10 by field with 1 times the square root of 1 minus 0.16. When you do that out, should be 9 cm. And the last one, we have a 15 by 15 with a 9 by 7 block. So the total field is 225. The blocked field, 63. Take a ratio. .28. So when you do the equation, it's 15 times the square root of 1 minus 0.28. So your answer on this one should be 12.7. Number 12, the percentage depth dose for an 8.3 cm field at a depth of 10 cm 100 SSD for a 4 MV beam. We need to use interpolation for this because I'm asking you what an 8.3 field is. I could easily go into my tables for percentage depth dose, and I can see for 4 MV beam, it offers me percentage depth dose for field sizes of 5 by 5 or 10 by 10, but nothing for 8. So this is where we need to do interpolation. So field size, percentage depth dose, it gives it to me for 5 and 10, but it doesn't for 8.3. So my percentage depth dose at a depth of 10 cm with a 5 by 5 field is 57.2. For the 10 by, 62.1. My next step is I'm going to take 62.1, subtract that, 57.2 from there, and I want to take a ratio. I'm going to multiply that by a ratio of the difference between my first number and what I'm wanting, 5 and 8.3, which is 3.3 over the total range, which is 5. And when you do that out, you should get 0.66 times 4.9, which equals 3.23. I'm then going to take that 3.23, because that's the difference, and I need to add that to my initial percentage depth dose. And my new one, percentage depth dose, is 60.4%. 13, let's do another interpolation. So the percentage depth dose for a 6.7 field, 10 MV beam, depth of 15 cm. So I look at my chart. Now I need to look at it for the 10 MV and make sure when you're looking at your tables or your charts you've got the correct energy. And the field sizes it offers are 5 and 10, and I'm in between there with 6.7. My percentage depth dose for the 5 by 5 is 53.7. For the 10 is 56.8. So the first thing I want to do is 56.8 minus 53.7, and I'm multiplying that by first the difference between my first two numbers, which is 1.7, over the total range, which is 5. 0.34 times 3 equals 1.05. I'm then going to add that to my original percentage depth dose to get my new one, 54.7. 14. We have a 12 by 12 field, depth of 7, 10 MV beam. We're going to interpolate again, percentage depth dose. So for that, I want to go in between 10 and 15. So percentage depth dose for a 10 by field size is an 82.5. For the 15 by, it's 83.1. Again, we're going to find the difference. We're going to multiply that by the range of 2 over a total of 5. So 2/5 is 0.4 times 0.6 equals 0.24. Add that to your original percentage depth dose, 82.7. And the last one, percentage depth dose for 17 cm field, depth of 9, 15 MV. Let's interpolate again. So field size would be, if it's a 17, we're going to go between 15 and 20. Percentage depth dose is 80 for 15, 80.3. So the difference, multiply that by, there's two difference there, a range of 5. So again, 0.4 times 0.3. So 80 plus 0.12, 80.1. 80.1 is your new percentage depth dose. Number 16, a patient's spine is treated with a single 6 MV beam at a depth of 5 cm, 100 SSD, field size of 5 by 30. Patient is 20 cm thick. The dose at Dmax is 200 centigrade. So the first one in A, I'm asking, what is the percentage depth dose at the depth of the spine? What is the percentage depth dose? So let's first put our formula in here and see what we have. The patient's spine is treated with a single beam at a depth of 5, 100 SSD, field size is 5 by 30. The dose at Dmax is 200. So I know my Dmax is 200, but I don't know anything else. I'm going to find out what my percentage depth dose, so that's unknown, but my dose at depth. The first thing I need to do is get a equivalent square, because I have a 5 by 30 field here. If I want to look up percentage depth dose, I have a rectangle field. So the first thing I need to do is find the equivalent square of the 5 by 30. So using Stirling's formula, I come up with 8.6. So now I have that. Now I want to look up my percentage depth dose. I can use my table to look it up to see what it is at a depth of 5 for a 6 MV beam. But again, I'm going to look at my table for that 6 MV beam, and it doesn't offer percentage depth dose for 8.6. So what we're going to have to do is interpolate. So with an 8.6, we're going to go between 8 and 9 on that 6 MV beam. We know for 8 it's an 86. For 9, 86.5. Again, you're going to do your subtraction, and you're going to come up with 0.3. You're going to add that to your original percentage depth dose of 86, which will give you 86.3 for your new percentage depth dose. So I found my percentage depth dose for this patient at the depth of the spine. Now let's carry that on to B. What is the ratio of the exit dose at a depth of 20 to the dose at the depth of the spine? Now, I can look at my percentage depth dose. I want to use my percentage depth dose again, but I need to know what it is at 20 cm. Earlier, I looked for the percentage depth dose at a depth of 5 cm. So again, we're going to have to interpolate using our table. So we're going to use the same equivalent square. We're using that same field size, but I'm looking at my percentage depth dose at 20. And for the field size of 8 by 8, it should be 38.3 at a depth of 20. And for the 9 by 9 field, it should be 39. When we do our interpolation, and it should be 0.6 times 0.7, which equals 0.42. I add that to 38.3 plus 0.42. Your new percentage depth dose is 38.7. But I don't want to know what the percentage depth dose is. I'm asking you what that exit dose is. And being that my spine is right at the surface, at the PA surface of my patient, I can use my percentage depth dose formula. Percentage depth dose equals dose at a depth over dose at Dmax. I know what my percentage depth dose. It's right here, 38.7. I don't know what my dose is right here at this depth, but I do know that my Dmax is 200. Because I said the dose at Dmax is 200, so x over 200. When you do the math for that, the dose at this depth of the spine should be 77.1. So this one has many steps, but the thing is what I want to know what the exit dose is compared to the dose at the depth of the spine. So it was 77.1 at 20 cm, and when we looked at the earlier slide, we saw that it was much greater. Part C, we changed our SSD to 120. The jaws were adjusted, so my field size still remained 5 by 30. What is the new percentage depth dose at the spine? What am I asking you here? What is the new percentage depth dose? Because I changed my SSD. Anytime you hear that, Maynard F. So you're going to write out your Maynard F formula and do the math. SSD1 plus depth, SSD2 plus depth squared. So when you do that out, 0.84, because what I used was, I'll just write everything I used down here so you have it. SSD 1 was 100, SSD 2, I'm going to change it to 120. My Dmax for 6 MV is always 1.5, and my depth is 5. So you just need to fill everybody in here, and you get 1.19 times 84 with a Maynard F factor of 1.01. That's just my F factor. I need to apply that to my original percentage depth dose. My original percentage depth dose is on A. We came up with it. It was 86.3. So I'm going to apply 1.01 to that, and I'm going to get 86.7 because there was a change in SSD. 17. You're treating a patient with a dose of 150 centigrade to a field 10 by 10, depth of 5, 6 MV, you realize after the treatment that the 15-degree wedge was accidentally left in. So what dose did the patient actually receive? So I need, for this equation, to get a dose, I have to apply the dose that they were given times my wedge factor. So I'm going to have to use my table to look up my wedge factor. So you're going to look up for a 6 MV machine, 15-degree wedge, 10 by 10 field. The wedge factor is 701. I'm going to take that factor and I'm going to multiply it by my dose, and I'm going to get a total of 105 centigrade. So if you think back, you always want to double check yourself. I prescribed them 150, but someone left a wedge in. That's telling me that that wedge absorbed some of that dose. So that's going to bring the dose down. If I had said I planned to give them 150 and there was a wedge in there, or the wedge was forgotten, then they actually got more. So, and you would divide. But for this, you're multiplying, your dose should be going down. 18. What is the dose rate in tissue at 1.5 cm for a 6 MV linear accelerator? Dose rate of 80 centigrade per minute at 100 SSD, backscatter factor of 1.025. Define the dose rate at Dmax, because 1.5 cm is Dmax for my 6 MV. Dose rate at Dmax. The formula for that is dose rate times backscatter factor. Because basically I'm getting it right here at Dmax. I have the output, I have how much dose is coming in, but I need to add to that any dose from backscatter, from scatter. Okay, so my dose rate, I told you, was 80. My backscatter factor, 1.025. Do the math, and you're going to get 82 centigrade. Last one, 19. What's the dose rate at 10 cm depth? 100 SSD. Use the dose at Dmax from the above question. The dose at 10 cm is 67 centigrade. Anytime I'm finding dose in tissue that's other than Dmax, I need to take the dose rate in air, which is your output, and multiply it by the percentage depth dose. I know that my dose rate from the above question from 18, my dose rate in air is 80 centigrade. I want to multiply that by my percentage depth dose. I didn't give you the percentage depth dose, but remember, percentage depth dose is a ratio of dose at a depth divided by dose at Dmax. And for this equation, the dose at my depth is 67. The dose at Dmax, which was on question 18, we figured that out to be 82. So percentage depth dose is 67 divided by 82. When you do that math out, your dose rate at 10 cm in the tissue, 65.36.